Converting differential equations to algebraic equations is a good idea because it makes the problem simpler and we can solve more complex problems. The finite element method is one of the most popular numerical methods to convert differential equations into algebraic equation, and it is used extensively in all different types of physics in engineering. So here is our problem. It's heat transfer in a slab. That's this one, and the governing equation is given by the heat equation in one dimension in this case. So the only dimension and the direction we're interested in is this. And so we also have two boundary conditions. One can be surface temperature given, and the other one is the symmetry. So it's del T del X at x equal to 0 is 0. So we need to only solve for 1/2. Now, in your differential equations class, you solved this problem and you got an analytical series solution. So this is my analytical solution, and we are not going to do this one. We're not going to use this one because this has a lot of restrictions. So the goal here is we will replace this differential equation with a set of algebraic equations. So this is a matrix that is of 3 equations, okay? And so these are linear algebraic equations where I can easily solve for the 3 unknowns. Now, I am showing 3 as just a representative. It doesn't pertain to this particular problem. In reality, you'll have many more equations typically, but the point is you are changing from a differential equation to a set of linear algebraic equations. This is our goal. Now, most of you know what is a finite difference method. And let's try to compare and contrast finite element method with this simpler method of finite difference that most of you know. So in a finite difference method, we divide the domain into nodes, and we solve the equation at the nodes to get the solutions. These are my solutions at the nodes, and then once we get the solutions, then we decide on interpolation in between. In a finite element method, it is in an analogous way. It is also the domain is also divided into the nodes, but here it's not the same nodes. Here the nodes and the distance at in between, they are together as an element. So nodes and the distance together, the distance in between together makes an element. But also when we build the method, the interpolation between the nodes is built in. So as you can see, the solution is going to be looking like this, and this is built into as we develop the method. So now, before we do this, let's have the big picture of what we will go through. We will break up the domain into elements with nodes. Then we'll take one of these elements and discretize the spatial derivative. That's this one, the spatial derivative. And then we combine the equations for all the nodes. Then we discretize the time derivative and then apply the boundary conditions, and finally just to make ourselves feel comfortable, we'll plug in numbers. So that's the step we're going to go through. So first is breaking up into nodes and elements. And so this is a 1D problem. So this is my domain. And I'm going to break this up into 5 nodes. That means 4 elements. 4 elements and 5 nodes. And now we're going to work with one of these elements. We will discretize the spatial derivative, that's this one, and convert it from a differential form to an algebraic equation. For one element, and we're going to do that for one element. So for one element, it has 2 nodes, so there are 2 unknowns. And our goal is to get the 2 algebraic equations. We will do this using 3 steps. So first, we assume a straight line solution between the 2 nodes, and then minimize the error to get the 2 needed equations. Okay, so we'll go through these steps now. So again, we are trying to solve the heat equation, and here is the geometry with all the elements. These are the elements here, and on the right we have enlarged one element. So let's say between 3 and 4, this element we have enlarged. So this is like 4, and then this is like 3. Okay, so for this element we have the unknowns as the temperature TL bar on the left node, and then TR bar is the value of temperature at the right node. These are unknowns. These are what we are trying to solve for. So these are unknowns, and in between TL and TR there is a linear interpolation. So values in any location in between can be found by simply linearly interpolating. So now this is my solution that we are trying to compute. I have superimposed the true solution, which of course is an unknown, but I have superimposed that in there, that just to contrast what we are going to compute with the true solution, which is an unknown. Now, there's no reason that this solution that we are going to compute, which would be some sort of approximate solution, would be exactly equal to the true solution. In general, they will not be. So the shaded area, this shaded area, that's the difference between computed solution and the true solution, is the error. This error can be positive or negative. Okay? So now we try to minimize the error to get to the needed equation. This is the sort of the second step. So again, the true solution is something we do not know. We will only compute an approximate solution, T bar. So the error is this shaded zone. And let's see how we can write this. So the true solution is given by, of course, my differential equation, and T bar, the bar is for approximate solution. So T bar is an approximate solution. So the error, that's the shaded zone, is given by the difference between two. So if they are exact, then it will be 0, and my this equation will give back my equation that I started with. Okay. Otherwise, in general, it will not be 0. So this epsilon tilde is not going to be 0. And so we want to make this error 0 on the average. Now, if we just do the average, meaning we add up all the errors here and here and set them equal to 0, which would look something like integral epsilon tilde dz equal to 0, this is not a good idea, because then we could have a lot of negative error and positive error together. It will give 0, but there will actually be a lot of error. Instead, we use this weighted average. So the weighted average looks something like this. So instead of just epsilon tilde dz, we multiply by these weights. We will soon discuss where the weights come from, but it's important to note, very important, that error is not made 0 at every location. So we're not going to have a solution. This is what we are going to have, that we will match at every point. This is not possible. So we will have to accept some error. This is the fundamental source of error in this kind of numerical computation. Before we get into the weights, we just develop the equation for interpolation. This is typically something we do in high school. So we just want to have an equation to this line. So let's write this from these two similar triangles. I can write T bar minus T bar is any temperature, T bar here at position Z, and so I write T bar minus TL bar over Z minus L is equal to this part, which is T R bar minus TL bar over this total distance R minus L. Okay, so this I can simplify as T bar is equal to TL plus Z minus L over R minus L times TR bar and TL bar. And further simplifying, putting the TLs together, TL 1 minus Z minus L over R minus L times TL bar plus Z minus L over R minus L TR bar. And so if I just do the subtraction, then this is what it looks like. So TZ, temperature at any location inside this element, is written in terms of the left nodal temperature and the right nodal temperature. This is just a fancy way of writing the interpolation function. So you are interpolating between the left value and the right value depending on where you are. Okay, so we can write this in just making things simpler in terms of doing the algebra. We can call this part as PL and we can call this one as PR. Why PL and PR? Because in general, in a much more complex finite element development, these would be polynomial, of other order. So here it's just a polynomial of degree 1. It's just PL is equal to R minus Z over R minus L, and PR is Z minus L over R minus L. So they are just really equations for line. And so if I plot these, they look something like this. So PL at Z equal to L, it is 1, and so it goes from 1 to 0, and PR goes from 0 to 1. So polynomials are also called the Lagrange shape functions, which we don't need to get into any more details. So back to the definition of error, we want to make the error, that's these, to be 0 on the average. Okay, so this gives me this equation, and then we want to use two different weights. The two polynomials that we just defined, we're going to use those as the weights. So by using those two different weights on this, I get two equations. So now I want you to simply see that we solve these two equations for the two unknowns, TL bar and TR bar, which are the only two unknowns for one element. So elements have two nodes, and those two nodes are these two unknowns. So two unknowns, to solve for them we need two equations, and these are the equations. And the way we got the equations was by making weighted average of the error to be 0. So the last part is to algebraically simplify those two equations. It's nothing but very simple integration and stuff that you did in sort of the first course in calculus. So to repeat then, we're going to plug in this PL equal to this thing. We will plug in here, and we will simplify the equation. Likewise, we will plug in PR in here, and then we will simplify the equation. So those two equations again, and we're going to substitute for PL, PR, but we are also going to substitute for the temperatures using our approximate solution. So our approximate solution is this. We will try to find this TL and TR, and then in between at any location we will interpolate. So this is my approximate solution. So this also needs to be plugged in to both of those terms. So let's see how we do that. So for the time derivative, then you notice that PL here and PR, they're not really functions of time. They don't change with time. So if I take the time derivative of the solution, then PL comes out, and we get del TL del T and del TR del T. So TL, TR are the nodal temperatures that will change with time. So the spatial derivative, on the other hand, I can write del T del Z as TL bar. It comes out. TL bar is the temperature at that location, so it's not changing with location. That's the temperature at the fixed location. And then PL, as you can see, it is a function of Z. So I can write del P L del Z, likewise for TR bar and del PR del Z. So basically we want to plug in things into this equation, del T bar del T minus alpha del square T bar del Z square dz equal to 0. We want to plug in here two things. One is PL equal to R minus Z over R minus L, and also T bar is equal to PL TL bar plus PR TR bar. We just want to plug in both of these into this equation and simplify. That's all we're going to do. Okay. So if I plug in for T, then as we already did in the last slide, del T bar del T is going to be PL del TL del T plus PR del T R del T. This is the trouble of using PowerPoint, is we are repeating some of it. So if I plug this term in here, this is the term that we plug in here, and PL. Integral L to R, when you plug this in, because del TL del T is not a function of Z, so that comes out. Okay, and we get PL from here, and then another PL from here, so it's PL square dz. That's the first term, and then the second term would be plus del T R del T and integral PL PR dz. Okay, so that those two just comes from the first one, this one here, and then the next one is minus alpha PL del square T bar del Z square dz. Again, it's all between L and R is equal to 0. So this second term is kind of troublesome because we don't have something for the second derivative. So let's see what we can do. Okay, so to convert this second term, you see I can write del Z of PL del T bar del Z is equal to a PL del square T bar del Z square plus del PL del Z times del T bar del Z. Okay, and so if I bring this guy that I need to the left hand side, PL del square T bar del Z square is equal to del Z of PL del T bar del Z minus del PL del Z times del T bar del Z. Okay, and so then if I integrate both sides, so now I integrate both sides from L to R, then you see this is the term that I needed here. This is the term that I needed here. And so I now I integrate out this one, and so this gives me PL del T bar del Z at R, because it's del Z integrated over del Z, over dz. So then I get back this function at R and then minus at L, del T bar del Z at L. And then for this one, it's del PL del Z times del T del Z. I can write from here as a TL del PL del Z plus TR del PR del Z. Okay, dz. And so now you see this guy PL at R is 0. If you look at this, PL at R is 0. So this first term goes away. So it's the next term minus PL del T bar del Z at L minus, then here we see it's TL bar integral del PL del Z squared dz minus TR bar integral del PL del Z del PR del Z dz L to R and also L to R. That's as much as we can put it on this page, so let's stop here. Okay, with the limitations of PowerPoint, unfortunately we have to rewrite some of the stuff. So the equation, that one of the two equations we got for solving for the left node and the right node is this one, PL del T bar del T minus alpha del square T bar del Z square dz equal to 0. This is one of the two equations, and we were plugging in for PL and T bar, but we only have plugged in for T bar so far, and from there we got this equation, del TL del T integral PL square dz. So this is what we got part way, plus del T bar the TR bar del T PL PR dz L to R minus alpha PL del square T bar del Z square dz L to R equal to 0. And then we just spent quite a bit of time trying to simplify this term. So the final equation we got there is del TL del T PL square dz plus del TR bar d del T L to R PL PR dz plus alpha PL. This is the part that we just did. I'm substituting that del T bar del Z at L plus TL alpha L to R del PL del Z squared DZ plus TR bar alpha and L to R del PL del Z del PR del Z equal to 0. So where I simply have substituted what we derived in the last slide for this term, so we got this equation. So this is one of the two equations that we'll solve to get TL bar and TR bar, which are my unknowns. Okay, so let's not forget that. So now notice it has all of these terms like this, but what is PL? PL is simply Z minus R over L minus R. So R and L, they are constants. So this is a simple integration. So let's do one of these. So let's do PL square dz L to R, which is equal to Z minus R square over L minus R square, plugging in for PL, okay, and dz is equal to L minus R square and then integral L to R Z square minus 2 ZR plus R square dz, and let me try to clean some of these, is equal to 1 over L minus R square, and the integration of this will give me Z cube over 3 minus Z square R plus R square Z between L and R. And so that, if you plug all these in, okay, let's do one of these. 1 my L minus R square, and you get R cube over 3 minus R cube plus R cube. As I plug in R, then I plug in L, minus L cube over 3 minus L square R plus R square L. And that's equal to 1 minus L minus R square times if I take 3 in the denominator, then I can write R cube and minus 3 L square R, and so minus 3 L, yeah, so minus 3 L square R, that's this term here, sorry about that, plus 3 R square L and minus L cube, and these two cancel out. So if you recall, this the numerator inside the bracket is L minus R cubed, okay, over 3. Okay, so this is then equal to minus L minus R over 3 equal to R minus L over 3. So this term, you notice, even though it's sitting there as something little bit complicated, it's nothing. It's something we can integrate out, and it's just equal to R minus L over 3. So the point that is that has to be made now, instead of going through all of them, I want you to see that these terms like this can be integrated out, and you'll have a simple value like this. R minus L is simply the length of the element. So in case you don't believe me, let's do another term that looks quite different. So integral L to R, and just trying to keep things separated, L to R del PL del Z del PR del Z dZ, and that is equal to L to R. What is del PL del Z? Del PL del Z, if you look at this expression, del PL del Z is just 1 over L minus R. Okay, and similarly del PR del Z, if you plug in for PR, then you get R minus L dZ. Okay, so what is that equal to? That's equal to minus L to R, R minus L square dZ, which is equal to minus R minus L if we integrate it out, and then R minus L square, which is minus 1 over R minus L. So now I hope you believe me that all of these terms can be integrated out, each one of them. Okay, so the two equations that we got by doing weighted average equal to 0, those two equations, we have been transforming one of them. So this is the first, this is the one that we were working on, and so if we plugged in some of the changes that we did, we have shown already that that one transforms to this equation. We also have shown that these guys can be integrated out. I haven't done the integration here. I put them in here to keep it general so far, but this equation became this one, and then if we go through the same process, then this second one is going to become this other one. So let's not again keep let's not lose track of what we're after. We want to solve for TL and TR. Those are my unknowns. So two unknowns need two equations. We started from these guys, and then now we have these two, the two in the bottom. Okay, and so in the next slide we're going to simply write these two equations in a matrix form, and we will hold off on actually integrating out these terms, but we know we can. So here we write those two equations for the two unknowns in a matrix format, here. And those are the two equations that I just showed in the previous slide. And if we integrated out these, then it would look, the two equations would look like this. So you see, these things are known. This was my H is my R minus L. This is known. So this is the distance between the nodes that I choose. And in something like this, alpha is the thermal diffusivity. So that's a parameter that's given. So all of this stuff is known. Okay. So we don't know these two, that we will come back very much, but this other stuff is known. So this is my two equations. So these are my two equations for the two unknowns TL and TR. Okay, so two equations, two unknowns for one element. And so I can write it symbolically for that element. So E for element. So this dt dt, so this array of the derivatives, I can write it as dt dt matrix, and then this I write it as C matrix, this I write as K matrix, and this is again T matrix, and then this is my right hand side. So this is my equation for one element. We're going to see that it's going to look similar when we collect for all the elements. So the hard part is done. We have two equations for two unknowns for one element, and of course it interpolates in between to get any other temperature. But now we're going to combine equations for all the elements. So what we have now is for one element, and we're going to now add all of these other elements together. So first we will try to combine the equations for two elements, these two. For element 1, I write the two equations, and here, just to make it look simpler, I have done the integrations of those, the integrals. Okay, we could keep it that way, or we would come back to those integrals, but for now I have integrated out. So those are the two equations, and you notice that the two unknowns are, of course, this T1 bar. They should all have bars, T1 bars, but then there are additional unknown. This guy, we don't know what to do with this, and then this guy, we don't know what to do with these. So the to solve for T1 and T2 bars, we need two equations. We have two equations, but we have additional unknowns. So what to do about them? So let's write the equation also for the next element. That's element 2. So this is element 1, this is element 2. So I write for element 2 similar equation, very similar ones. So again, you get two equations. Now you notice that element 2 has this term that is same as in element 1, but with an opposite sign. So now we can eliminate these by adding these two guys, meaning adding these two equations. But if we do that, then let's see what we get. So if we combine the two, then we get this equation where this the middle one, because those two are added, it's become 0, and these, since these two equations are added, we have only three equations. The first one, the second one, which is add these two added together, and the third one, and that's what gives me this 3 by 3 matrix with the three unknowns as T1 bar, T2 bar, T3 bar. These should all have bars in them because they are my approximate result. And so then I no longer have these guys. You notice these two guys were unknowns. I no longer have them, but I still have the ones at the end. We have to do something about those, but for now let's keep. And so just know that there will only be the two last ones left. Otherwise, so for element 3, when we write the two equations, the first one would cancel out with this one. So all the middle ones will cancel out and we have the very last one. So if we put all of the elements together, so let's say there are these n nodes. So n nodes will have n unknowns. Okay, so these T1, T2, T3, T4, Tn, these are all the unknowns. So we have n unknowns, and so the number of elements would be n minus 1 element. So if we divide the domain into n nodes, we get n minus 1 element, and so we have this matrix that is n by 1. So n are those temperature values that we need to calculate. So Tn, Tn minus 1, this is T1, T2. So those are the things we need to calculate, and what I am showing you here is simply the equation from the last slide, but expanded to more than 2 elements. Okay. So now we get into discretizing the time derivative. And because you recall that we still have this kind of a term, dt, dt, d1. Okay. So the time derivative is still there. So now we will discretize the. So back to the equations for just 2 elements together. So 2 elements together, there are 3 unknowns, T1, T2, T3 bars, and so we have 3 equations. Now this time derivative, we want to convert them. So I can write the time derivative in a very simple way, like we do in finite difference, just for the time derivative. So dt, this I can write as T1 bar at t plus delta t minus T1 at t over delta t. So that's the simple way of writing out the time derivative in terms of values using finite difference. So this is also an approximation. Okay. So if I write all of the derivatives this way and then simplify, notice that we already have temperatures in there. Okay. And so those temperatures, let's say we assume them to be at time t. Okay, so if we substitute these guys in there for derivatives, and then if we simplify again, and you can convince this yourself, but you can see clearly that if I substitute in here, then we would only have T1 at t plus delta t and T1 at t. Then we collect all the terms that have T1 at t, and then we get this equation. So you notice what we have done. what is T1 at T plus delta T? That's the temperature at the next time step. And so that's on the right hand side. Those are my unknowns to be calculated. And on this side is T1, temperature at node 1 at time T, the previous time step, which we know and which we use to calculate the temperatures at time T plus delta T. And we can march on this way. So you notice something really big has happened. So we started off with the heat equation, del T alpha del square T del Z square. We didn't go through the series solution or some other analytical solution procedure, but we converted them like we wanted to. We converted them into algebraic equations. So these are just algebraic equations. All these things are known, so we can always solve for T1 at T plus delta T, because everything on the right hand side is also known without these guys. We will show you that these also can be found, but for now assume they can also be found. So everything on the right hand side is known. So this is a big deal that we converted a differential equation into just algebraic equation. Now instead of just playing with these two element equations, just 1 and 2, we will go back to the more general one with all the elements. So the one with all the elements in there that I had showed earlier looks like this, with all the elements in there, and they should all be the approximate values. Okay. Okay, so I can write this entire matrix now. So this is for all elements together, for all elements together. Okay, so that's why it has n equations for n unknowns, T1 bar, T2 bar, and so on, Tn bar. Okay, so if I write this in symbolic form, then this I call the C matrix, and this is the dt matrix. So this would be n by 1 because we have n unknowns, and so then this matrix would be n by n, and then likewise this is my K matrix, and then of course T matrix is again n by 1, and so the right hand side would of course have to be the same, n by 1. So this is my equation for the entire system. Okay, we now go back to the full system of equations to change the time derivative. So this is the full set of equations, and it still has the time derivative in there, which we now want to change. Now there can be many ways of writing the derivative. One we already tried a few minutes ago. The two common choice for discretization is, one can be forward. This is the one that I just did a few minutes ago. So the forward one, dt is simply t at t plus delta t minus t at t over delta t, and these temperatures are taken at the current time step. And from there, if I do the algebra, then I collect all the terms related to t plus delta t on this side and all the terms related to temperatures at t on this side. And so you notice now this is a set of algebraic equations where everything is known on the right hand side, and we are solving for these temperatures at our next time step. Everything is known because, as I already discussed, these quantities inside the matrix, they are known because we know what the size, the element size we chose, and so on. Likewise, we know what is the time step. And so, and then we also know the temperatures at the current time step. So from there, we can find temperature at the next time step. So this is a set of algebraic equations, like I showed in the matrix form before. The other choice of changing the time derivative is this way, where this temperature here is taken at the time step to be calculated. That makes it implicit. That makes it a bit different. So again, if we collect all the terms together for temperatures at T plus delta T and temperatures at T, then the final equation looks like this. This is a bit different from here, but the calculation behavior for them can be quite different. So whereas this one can often can become unstable, this one is typically quite stable in calculations, meaning it will not give garbage that easily. We can take larger time step. So these details we're not getting into. I would like you to see that the derivative, the time derivative, has been transformed or can be transformed in one of two ways. After that, it is nothing but an algebraic equation. So then in here, our heat equation has been completely converted into an algebraic equation. So we just now need to solve a set of linear equation, simultaneous linear equations. Now that we have a set of algebraic equations, so we have converted everything from the spatial derivative and the time derivative to a set of algebraic equations, we just need to apply the boundary conditions, which we haven't done so far. So just to recap, when we wrote the two equations for element 1, that's this, and then element 2, this, then we combined these two and we eliminated these two terms. This one and this one got together. When we added, they got eliminated. So we showed that all of these middle or the interior terms can be eliminated, but the first one and the last one are going to stay. So these are still unknowns, unknown and unknown here. Okay, so these are also, you notice they're at node 1 and they're at node 3 in this case for 2 elements. So it's this end. So if we do this for all the elements, then the last one is going to be node 5. So those are the boundaries. And so coincidentally, we have not even used boundary conditions so far. So we will use the two boundary conditions here and here to evaluate these two guys. So those are the ones that we need the boundary conditions for this two noded element. So we're going to go through three common types of boundary conditions. One is temperature specified, the other is heat flux, and the last one is convection, as you have seen in a heat transfer class. So the first one is this temperature specified. So for temperature specified boundary condition, you notice that the equation that we have, now this is of course for the two noded element, so these are the temperatures we are going to solve for. These are the unknowns. But notice, if this boundary temperature is given as it is here, then this is not something we need to solve for. So then the way this is implemented is we force this condition as one of the equations. So we replace the first equation by this one. So this basically says that T1 is equal to Ts, or the temperature at the previous time step at 1, which is a known condition. Okay, so this boundary condition is handled this way because this basically says that the for the boundary the temperature is already known, so you wouldn't be solving for it. So this is how it's handled. The next one is flux specified. So you remember, flux specified boundary condition is written this way. So this is the conductive flux is equal to the flux value given at the boundary. Now you notice, interestingly, in our equation the term already needs this gradient. It needs the gradient. So this works out very conveniently. So all we need to do is, from this we replace, del T del Z is equal to minus QS over K. So if we replace that for del T del Z in here, we are done. So let's see how that looks. So we just replaced that by this, and so alpha, as you know, is K over rho Cp. So this K here that is coming from here would cancel with this K, so I get QS. Or we can even show that in here. So alpha del T del Z is equal to K over rho Cp del T del Z, like I said. So this part of it is equal to QS, or QS, negative of QS. Okay, so we plug in. So then this part is known. It's now known. So that's how we do the flux specified boundary condition. Then the last one is using convection boundary condition. So this is how we write convection boundary condition, and we can choose to write this in a implicit way. We don't have to get into the details now, but we could choose as T or T plus delta T. We choose a T plus delta T, but you know the rest of the equation is very familiar with you. Minus K del T del Z is equal to H times T minus T infinity. So then from here I'm going to just replace. Again, we have alpha del T del Z is equal to 1 over rho Cp times K del T del Z. Okay, and this is the part that is given, okay, from this boundary condition. So we plug that in, and then eventually, if we do a little bit of simplification, then this term changes to this. So all of these things are known now. H is known, and then T infinity, the boundary temperature, this is something that is known. So this is now known. Okay, so that is how we handle the three types of boundary conditions. One of the most useful aspects of numerical solution like the finite element method is its flexibility to use many different boundary conditions. For example, the boundary condition, the temperature, surrounding temperature doesn't have to stay constant. And I'm going to show you an example of that. So here is a project from our class from the past. And the project has to do with hatching of eggs, turtle eggs in sand. So the eggs are at about this level, and it's in the sand, and there's some heat flux from the atmosphere that heats up the sand. So the temperature here depends on the heat flux at the surface. And why are we interested in the temperature? It's because whether the eggs will hatch into male or female depends on the temperature history that the eggs go through. So that's why we want to calculate the temperature here. Now, I am not showing you all the detailed physics of this. I just want to make the point. Let's say I want to calculate temperature at this location, so without bringing in other complications due to the egg being different from the sand and so on. Let's say I just want to calculate the temperatures here, and the problem is in this boundary condition, in this convective boundary condition, let's get rid of the radiative flux part. So in the convective boundary condition, this air temperature is not a constant. In fact, it looks like this. This is the air temperature. So if the air temperature keeps changing with time, how do I calculate the temperature here? By the way, the solution looks like this, the average nest temperature. But how do I calculate that? I'll show you in next slide. It is hard to do this analytically. So here with the finite element method, this is very easy. Again, I am showing these equations because we derive them, not that these equations apply to this problem, but the form of this is certainly the same as would be for this problem. I want to draw your attention to this part that has the T infinity. Okay, so when I'm calculating temperature at time t plus delta t, so let's say this is my T and this is my T plus delta t. So when I'm calculating the temperatures here, I need the air temperature. So I can use the air temperature from here, for example. I know this temperature, so I use this value. And by using that, I calculate temperature at T plus delta T. Then the next time when I'm here and I'm calculating at T plus 2 delta T here, I just need to update. This is the only point for all the discussion is this T infinity. It's the discrete value that is needed just for that time step, for that calculation. So when I am calculating at this time step, I just substitute the value here at the previous time step. So in other words, I keep updating this value here, and the temperature automatically will be calculated for these conditions. In fact, you can see that. You can see the solution that was calculated by changing the T infinity continuously like this. So this is not possible. For example, if you contrast this with analytical solution, this is not possible. So for the condition of a convective flux given, okay, for this condition in a semi-infinite region, I can calculate temperatures using analytical solution. Okay, so this is very possible, except this assumes T infinity to be constant. So T infinity has to be constant here. T infinity cannot be this. So this analytical solution is not flexible. And that is the biggest advantage of a numerical method like the finite element method, that it can track, let's say in this example, boundary conditions, for example, that can vary any way it wants. We just need to know what it is. That's all. And then we can use it. So this final step is not much else. We're done, but we just want to plug in numbers and just to make us feel comfortable with the final product that we got. Okay, so this was our original governing equation, the heat equation, and we converted it from the differential equation to a set of algebraic equations. Okay, so even though it's algebraic equation, with all these symbols everywhere, it may not be obvious that we have achieved something really great. We have achieved something that now is really very kind of easy and straightforward to do the next step. It may not be obvious looking at all of these symbols everywhere. So I just want to plug in numbers and to have our eyes believe that yes, indeed, it's kind of simple thing right now, at least for this small system of equation. So you notice what we are trying to solve for. It's temperatures at time t plus delta t. So for an initial temperature of 37 degrees, okay, for T infinity, the ambient temperature of 70 degrees, H, the heat transfer coefficient of 20, the thermal diffusivity of 10 to the minus 7 meters square per second, density times specific heat as 10 to the 6, delta H, this is the, we are doing this for a slab, and so we are dividing the domain from the line of symmetry to the surface. We're dividing it into a number of nodes. So delta H is the size of the element, which is same as this H1. So we choose that, and we choose 1 second time increment. So if we choose all this, then we plug in to all of these values, then it looks like this. Now would you believe that it's a easy thing to do? So we just have to solve these three equations for the three unknowns. Temperatures at the three nodes at time step 1, and then this would be used to calculate the time step 2, T2 or T1 at 2, that will go to T1 at 3, and so on. So at different time steps. And so it's really a simple process right now. Now, of course, very large systems of equations, it's not simple, but at least conceptually, we have gotten completely out of the PDE solution to solving a set of linear equations where these are the variables that we'll solve for. So the form of it is our most common AX equal to B. So we solve for X. So we now summarize everything we did in this building up of the finite element method. So first is we took the differential equation and converted into algebraic equations. And we did that. That is the process of building the finite element equations. And we did that by first breaking up the domain. So the domain in this problem is this the thickness of the half slab. It's symmetric, so we need only half slab. So we break it up into nodes and elements. That was the first step. Next, we discretize the spatial derivative here for one of the elements. So we did that. And then we combined equations for all the elements. And then we discretize the time derivative. And then we applied the boundary conditions. And that's basically it. And then we plugged in numbers just to see how things go. So there are some very important points worth noting of this method. First is it is discrete. It solves only at the nodes with interpolation in between. So it does not solve in the sense of an analytical solution. Then, and also this solution is kind of approximate solution. However, the error that we make can be improved as much as we want. How do we improve the error? By having more nodes or smaller elements. So more nodes, less error, and also smaller time steps. Then flexibility is built into because it's numerical method. So we can have initial condition that can vary with position. We can have boundary conditions that can vary with time. We can have properties that could change as a function of the process, like a thermal conductivity changing with temperature, and the entire domain can shrink or swell depending on the process. So all of these flexibilities are built in, and this is the reason why numerical methods have become default for solving real-world problems, and finite element is kind of the king of that. More of the physics are built into codes for solving different physics. More of those physics have been solved using finite element method than perhaps any other numerical method.